So hello everybody, so welcome to another tutorial, welcome to the Epidemic Simulator tutorial. So what will this all be about? Today we will talk about the Epidemic Simulator, so how we can simulate epidemics, just like the COVID epidemic that you've heard of, or whatever epidemic you like to, with the simulator that I've written this year. Well, what is this all about? Why am I talking about this? So we recently published an article, so I'm co-author of this article, which is about the SARS-CoV pandemic, and in order to write this article, I have created a whole simulator here, or we've written a whole simulator together, and so I want to make a little tutorial. So how can you use and how can you profit from the simulator? Because it can do way more things than what is described in this paper. And I thought, if you're running your own epidemic, if you're an epidemiologist, if you do things that are close to what we're doing here, you should use it, and you should cite us, of course, therefore, we have a little video on epidemiology, let's say it like this. So what is the Epidemic Simulator, and how does it work, and what can you do with it? So the Epidemic Simulator is a little C program which allows you to simulate SEIR modeled epidemics. Okay, so what is SEIR for those who are not in the field of epidemiology? So this is a level of theory to model epidemics, or in general. You will see what this is all about. For those who are in epidemiology, they will see, that's old stuff. Nobody's interested in that anymore. That's very easy to do, but the specialty of the simulator is that, it allows multiple competing variants. So you can have multiple strains of your epidemic, and they can compete with each other. So this basically means that if you're infected with one variant, you get some kind of you get some kind of you become immune against another variant, and we can do this for multiple classes. So multiple classes means you can cut your population into different subjects. Let's say it like this: you have like a very high infectious class and a less infectious class, because some of the people are confined, the others aren't, and they interact a bit with them, and so you have different parameters going on in these two classes, and so you can do this with multiple variants, multiple infectious classes, and all at the same time, and run the whole epidemic. That's kind of the idea behind this kind of system here. And one way to have these different classes is, for instance, you have different age groups. So you have children which are more susceptible maybe to infection because they go to school or something like this, and you have elderly people which recover less fast from the epidemic, and with our epidemic simulator you can model all of this, and it's all pre-programmed for you. You just have to put the right parameters in there, and we will show you today how this works. So first of all, for those who are not into epidemics, and even for those who are into epidemics, what is this SEIR model, and then how do we improve on this in order to get these multiple competing variants going, and in order to get these multiple classes going in the same simulator, and how do you run all this together? So first of all, the SEIR model. So the SEIR model is a 4-state model. So your population is distributed in either of these 4 states. Okay, so part of the population is either susceptible, so this means basically never had the disease, or it's not immune against the disease. It's susceptible to be infected, but it's not infected. It's well-being, and nothing happened so far. At one point they might get infected, but when they get infected in this model, this model models this in a way so that you can be infected but not yet contagious, because you don't have enough bacteria, enough viruses, or enough parts, so that the disease still has to develop, so in order to be in your body, in order so that you can infect someone else. So people flow from this S state into this E state, and as the disease develops in them, they get infectious, so they get into the I state. So here they are infected and contagious, of course, and once they conquer the disease, well, they are re-established and immune. So when they are in this R state, they are not susceptible, and they're immune, and that's kind of the way it works. Here we in our system we have like a closed loop, so you can be immune, and just for some time, because after some time you lose your immunity and you become susceptible again. So we have some kind of immune waning in here, which allows you to come from this R state back to the S state. Yeah. And so how does this? Right now you ask yourself, okay, 4 states and people flow from one state to the other. Well, yeah, how does this all work? Well, let's continue a bit. So you have rate constants, and this rate constant, so this basically gives you the instantaneous flow, yeah, of people from one state to the next. Yeah? Let's call it like this. Yeah. And so what happens here is that, well, of course, individuals flow, as I said, from one state to the next here. And the big deal here is, well, how does this work? So you have this beta constant, and this beta constant basically tells you, okay, you have S people that are susceptible, and people that are infected and contagious, yeah, because if they're not contagious, well, they can't infect anybody and nothing happens. So if there are no I people, nothing will happen, because nothing will pull them from the S into the E state. No, that's the way it is. Yeah, and so you have beta times S. So it also depends on how many people are susceptible, because if everybody has been recovered and is immune, well, nothing will happen either, because there are no susceptible people in here. Yeah? So that's why you have basically a constant, the number of people in S, the number of people in I, and this is the instantaneous pull into E. Yeah, and why instantaneous? Because of course this is not static, because if the people are pulled out of here, the S drops, no, or I increases, and that way this here is modulated and will change in time, and so this is just for instantaneous at a certain point in time. The flow from one point to the next, and you have to write this as a differential equation and integrate that so that you get the whole trajectory of all these 4 states, and this is what we are interested in. So for example, you want to know in time how many people are infected. Well, you take the E and the I compartments here and you add them together, and you plot them over time as you run your simulation here, and then you get the epidemic out of it. No, that's what we want. Yeah, and so we have this constant, so we have this beta constant, we have this delta constant, which tells us, well, delta E, well, depending on how many people are in E, how many people flow into I, no? Here, how many people flow into R from I, so how quickly people are re-establishing themselves. No, this is basically this gamma stuff here. So the bigger gamma is, the faster they re-establish. So the shorter they stay infectious, the shorter they are sick. Let's say it like that. No, that's how it works. Yeah, and then we have this eta constant, which is the immune waning. which basically makes it so that people who are immune against the thickness, well, they lose their immunity because either the virus mutates or whatever happens, or just their immune system doesn't keep up. So they become susceptible again to capture the disease. Yeah? And these are, of course, mean constants over populations. And as we said, well, we have multiple classes, multiple population classes, which can have different constants here. And which can interact, of course. So this interaction is always modeled in this beta term here. And so we have, how does this work? Yeah? As I said, we have multiple competing variants and we have multiple infectious classes. Yeah? And so what we do here is we have a simulator which is multivariant and multi-class, and so this means we have multiple SEIR cycles running in parallel. No? So you have this here per class and per variant. So you have a matrix S, you have a matrix E, you have a matrix I, a matrix R, with different rates flowing from one to each other, and with interactions between each other, which are modeled basically in this beta term here, which gets very complex, and this way we model this. Yeah? So to keep this up, let's get first into how we do this. So we have basically, as I said, we have multiple SERI cycles running in parallel, and let's start with variant interaction. No? So if this SERI cycles, you have them here, so you want to have that. You have two cycles because you have two variants, for instance, yeah, and just one class. Let's call it like this, yeah, in order to simplify this explanation here. We have an epsilon ij term, and this epsilon ij term, maybe I will bring up here a second copy of this, so that we can watch this here with the full model architecture, so here you understand it a bit more easy. So we have this epsilon I in here ik term, and you see you have here a sum basically. Yeah, so what happens here? Yeah, so we have ij, so I ij, so I guess is the let's say the disease index. I just have to make sure that I'm not talking anything wrong here. KL, okay, L to M. Yeah, K, so K is a variant. Yeah, so K is a variant here. Yeah, that's the way it works. Okay, so you have ij matrix here, so one index basically for the variant, another for the class. So in this case here, I should be the variant index, J should be the class index. Yeah, and we see here so how this works. So this is basically what is pulled out of S, no? So you have, as we have it up here, we have S, beta, Si, so you have here S, beta, I, yeah, so you can pull, of course, you can't pull beta out, but this is basically what is subtracted in time dt from S, yeah, and this is what gets in, so this is this eta R, what comes into S, yeah, this is the change of S in time dt, yeah, okay, differential equation, no, so that's the way it's modeled, no, and of course we have these indexes because I told you we have a multivariant multi-class system, no, okay, so we're with this epsilon. And what I have prepared for you here is basically to get this here is you have these sums here, no? And you have basically what this does is, well, you get infected with one variant, so you get infected and you get pulled into E, which is basically modeled down here very easily. So you just have like S, beta, I, and here you don't have an epsilon, so this is the standard stuff. You get pulled in here into the E from the correct variant, yeah. And here using the second sum here, which is this K sum here, which goes over this epsilon here for index I. What happens here is you go over the second index here, no? And basically epsilon, so if you have beta E11, this should be 1, and so you get pulled out normally just as you're down here, no? So that epsilon becomes 1, yeah, in this case here. But if you're IK, so if this is not the same here, then you get pushed out of here, and as you don't get pushed anywhere else in, so you get pulled into R. So, which means that if you get infected by variant 1, this beta epsilon term makes it so that you fall for this variant 1, or for this variant, the one variant in question here, you fall into the E compartment, while at the same time using this epsilon parameter, which says maybe 0.8 or whatever kind of immunity it infers you that you get infected with this variant 1, pulls you out of the other S compartments using the sum, so of this S2 in this case here, and pulls you into R2, and the same of course for all the others depending on the case. So this is done using this sum here. It pulls out and puts you into the other. It puts you into the R compartment, so that you get this co-inferred immunology. Yeah. So I hope that this is clear. So you get infected by variant 1, you infer using epsilon 1, 2, you get an immunity for R2, and this is basically modeled with this Kn sum here, which basically pulls you out for the different variants. Yeah. Okay. Okay, of course your beta term here is very complex, and your IKL term, and it's getting complex, but that's the way it is. That's the way it works. Yeah. Okay. Okay. So this so far about cross immunity. Yeah. So we have this here. Yeah. Yeah. Not forget, I is the variant index, J is the class index, so maybe different age groups for J, I, different variants. And you see, using this sum here, you can infer with this epsilon parameter cross immunity. So yeah, okay, you got it. You're infected for variant 1, it infers your immunity to variant 2 by pulling you out of S2 into R2. Yeah, okay. And of course this works for n variants with epsilon ik. That's the way we do it. Yeah. Okay. Next thing is class interaction. So class interaction. You see, we have here these. We have here, let's say, different classes, and these different classes, they have a different susceptibility to the disease. Yeah. And this is written down here with this sigma term here, yeah. And so you see, you have your beta here, and as I said here, so this K is the here the index for the variant, and so you have a class to variant matrix here, yeah, which basically tells you, well, how strong or how much stronger this class is affected by that variant than the other one. Yeah, so you can really have per class, per age, you can say, okay, well, this age is stronger affected by the virus, has a stronger susceptibility to the virus than maybe children, for instance. So older people are more susceptible to the virus than children, if you model it like that. Yeah, so if you have two classes like this. Yeah, that's the way it works. So this is basically here with this sigma, yeah. So if you go to this beta, this R here is, here it's written out. This R is basically this intrinsic reproducibility of the virus, which is modeled. So you have this sigma here, which basically multiplies onto this R, so where you can model this R, where you can change it basically for age group, where you can modulate it per age group. Yeah. Okay. And you have, of course, in here. So this is basically the whole term, how to pull you out of this S into this E here, yeah. And we have here in this beta further we have besides this sigma we have this Cij and this J and L. So K here is the variant index, J and L are classes here. Yeah, this is done using this double sum here, so that you have J out, L you sum over here, so you sum over L and you sum over K as you've seen it before, and so you get J out, so that you have Sij. Yeah, that's the way it works. Yeah, okay, and so you have here this whole stuff here, this CJL, which is basically this contacts map. Yeah? So this contacts map is like this, is basically, well, how much people do interact with each other. So how many, let's say, how often one class gets into contact with another class, yeah, in one time unit. Yeah, let's say it like this. Yeah, and as I said, this is not symmetric, and so you have this n over nl terms in here, so to form this kind of symmetric here. And down here you have this rho term, which is also very important to know, because this rho term basically, this here is the largest eigenvalue of this auxiliary matrix M that we have to construct here, which also contains this susceptibility and this CJI, and here in this F you have the pre-infected and immunized fraction of each class. Yeah, so you have to parameterize this. So with the initial, let's say with the initial R, so how many people are already immunized at a certain point in time here, and you have to put this in there, and this here gives you an eigenvalue here. That you have, so you calculate the eigenvalue for each variant, because the K here is the variant index, yeah, and this here is JL, so these are the different classes, and so the largest eigenvalue you plug it in here, and this gives you approximate here this term beta here, yeah, so the largest, so this is basically the largest. How should I say it? The largest eigenvalue of this matrix here. Yeah, so how strong this pull here gets. Yeah? That's the way you have to do it. That's the way it's modeled. This way you get this let's say this interclass interactions into beta. Yeah, so beta is all about how strong it is using this RK term. This gamma term comes in here, so this is like, this comes from here, how fast you re-establish yourself, but that's not that important. What is more important here is that you have all these, let's say, this interclass interactions. So how susceptible is one class to each variant, and how much does each variant interact with each other in this beta term. Yeah? And this is done using this double sum, how you get pulled out in an instantaneous time out of this S part. Okay. Sounds very complicated, is less complicated. What you need to know is that you have a susceptibility that you can modulate in this model for each class that you have. And you can, of course, model the interactions between the classes. Yeah, and you can modulate them, and of course, this will then change the development of your disease. Yeah, okay. So far, so good. Well, you have then, of course, all these different compartments. So you have this for E and I and R, as it's just pointed out. So R is very easy. You don't really have here a differential equation because it's just what rests if it's not in all the other compartments, no? And that's basically it. So you then have just to integrate that, and you get a trajectory out for S, E, and I that you can plot then, and that we're basically interested in. Yeah, that's the basic story. So that's all we want. That's all we need. That's all we basically need to do. And so the question is right now, well, how? Let's get practical. How do you do that? How do you simulate your epidemic? How can you simulate the using this model here that I've presented to you? How can you simulate the multivariant, multi-class epidemic? In the model, there is also so if you read the manual, which is on the internet, there is also a part for vaccination. I just leave it out here because the vaccination is completely untested and probably wrongly implemented. So if you use this model, just use it without vaccination so far. I strongly encourage it you. Otherwise, you have to read the code or read the equations that are published with the documentation, and make sure that you know what you're doing. Yeah. So that's the way it is. So let's get practical. Let's run the simulator. Let me show you our little simulator. So the simulator is found on GitHub on my little GitHub repository. So let's fire up a browser and let's head over to GitHub in order to find our epidemic simulator. So I type here hashga and GitHub and SIAR maybe. SIER. So I called it SEIR so that you can easily find it. There's kind of, actually I made a spelling mistake, but then I didn't want to change it anymore. So, okay, so we have it here. So this is a model for multivariant epidemics, as I told you. So this is what we are doing today. And here we have basically the program. So you head over to this URL. I will bring it up here in a terminal so that you can see it. We will also put it into the description of the video. So you see here, this is the URL where you can find this whole code that implements all that, and which allows you to do a multi-class, multi-variant epidemic. Yeah. Okay, so let's download this. Let's get started. So let's clone this. You just clone this. So you need a Unix machine, of course, as for all my software that I've shown you so far, or you run this using Windows services for Unix maybe, but well, the easiest way this here is implemented. This doesn't need any external libraries. It's really cool. It's really like, yeah, you just download the C code. If you're basically more or less POSIX compliant, it should run. Yeah? I guess it runs on a Macintosh. It should run on any kind of Unix system, probably on Windows services for Unix if you have a GCC compiler or a C compiler or whatever you need. So I clone this here. And we have it here, so we have this SEI, so I know normally it's SEI, here it's SIE. Yeah, spelling mistake, but that's the way you will find it on the internet. No, that's the way it works. So we have here the SEIR multivariant epidemic simulator, and how to compile this. Well, it's all written down here. So you have here a little introduction, and here compilation with GCC. You copy and paste this here. So you copy this and we paste this here into the terminal. And if you're on a Macintosh, well, I'm not sure if you have GCC, but Clang probably works fine. So here I'm on a Unix machine, of course. This is my little Unix laptop, but a Linux machine, but my little Gentoo Linux machine. That here, of course, I have a GCC. So if you don't have a C compiler, as always, as already told you in the previous tutorial, a C compiler on a Debian machine, if you don't have a Gentoo machine, of course, or something like this, is apt-get install build essential, something like this, build essential. I'm just making sure that I write this correctly, no? Build essential. Yeah, so that's the way it's written. No, build essential. Away. Here we don't have apt-get. If you install this build essential, you get a C compiler, you get make tools, you get everything you need in order to run this. Yeah. So I will compile this here, and then I get an execute model binary out of it, and that's basically all we need. Yeah. So it compiles. Yeah. Fine. Done. Compiled, and then we just basically what we do is we parameter our model. No. So how do we parameterize our model? So we have here our model, and of course it has lots of parameters because we have this eta here, we have this epsilon here going on. No. We have this delta here, we have this gamma here, no? And we have this sigma here and the C that we talked about, and we have to parameterize all this. And in order to do this, it's very easy because the way it works is you supply a parameter file, and I supply with it a sample input parameter file. So let's go through this sample input parameter file. In order to see what will happen and in order to see how this works. Yeah? So here we have a sample input for an epidemiology, and as you see, so how does this work? So this is very well annotated, so we will walk through this here very quickly, and we might change some parameters and play a bit around with it so that you see what you can do with it. But that's basically it. Very easy to understand and very easy to work with it, and that's why I hope you will use this in your own tool. So this is a normal text file, so you can edit this with any text editor. Here I've opened it with Emacs. You can of course edit this with your editor of preference. So the way it just works is all these things have keywords, and after these keywords you put some numbers. If you use a space, it doesn't matter. If you use a hash, it doesn't matter either. Just keep the keywords in there. All the keywords are necessary. That's the way it is. And of course there are enough parameters necessary according to the variants and classes that you use. Yeah. So let's start with it. So runtime, of course, this is how long the simulation runs in your time unit. So my time unit here is days, so 730 days, so multiple years long simulation here going on of this little epidemic here, and then we have an error tolerance. So this is basically in the Ranji-Kutta algorithm how tolerant you are to errors. So the whole epidemic is integrated using a variable step size Ranji-Kutta algorithm. This is written out in the documentation. I won't get into details here. This is not a tutorial on how to use, how to integrate differential equations. This here is basically just the error tolerance that we stay in here, and we keep it here at 1e-8, I guess, for standard epidemics. You should be fine with that. Yeah. That's the way it is. Yeah? So you can keep this the way it is. Of course, this here is the runtime, how many days you want to simulate during your epidemic. And here it becomes interesting. So here it's like the number of variants and the number of classes that we have. So here we have two variants of the two strains, if you want to, of the same disease, or of two competing diseases, could be also that way, because the only thing that we have here with these variants is of course this epsilon interaction, so that one variant infers according to epsilon that you define in here an immunity to the other variant, and we can play around with that. Yeah, so we have two variants, three classes. Yeah, so three different groups. So here we have taken the parameters that are filled in here. This is for age groups in France. You can have different groups. So basically here we have three groups. So we have children, adults, and elderly. Yeah, if elderly are adults or not, that I'll leave it up to you. Depends on their mental state, maybe, I don't know. But sorry, don't want to discriminate anybody, but basically that's the way it is. Yeah? So we have like three different states. So let's say the young generation, middle-aged generation, and old-age generation. Yeah. Okay, so intrinsic reproduction rate, one bivariant. This is basically this R value here, written out here as R0. So this is this R basically here, which of course gets modulated also by this sigma value, but here the R is basically how fast. So this basically tells you how fast the epidemic grows. Yeah, it is written out here as R0 because what happens here basically. So if everyone is susceptible and you put in one guy who is infectious, well, he should be R more that should be infected next day. You know, so that's the way this works here. No. And so we have one bivariant. So if you have two variants, you have to put two numbers here, otherwise the program will crash. Yeah, that's the way it works. Yeah. Okay. Same thing, variant introduction date. So you can say, okay, the second variant happens to be in the later stage in the epidemic, so nothing will happen until this date. Yeah, that's basically the story here. Yeah, okay. For the second variant. Yeah. So if you have the second cycle. And you start with all people out in S, yeah, okay, second introduction 150 days later, S2 starts 150 days later. So this is basically when each variant will be introduced, okay. Total population, this is important for this N calculations here. Actually it's not that important, but this is like here you just put it in here. So this is France, yeah, 6.67 million people here. You put your total population value in here. Actually this is normalized, the value, I guess it's used, it's read, but so put the value here. It's not that important for the outcome because all the other values are basically normalized to 1, and also the output shall be normalized to 1. Yeah, and so you have to multiply it then by the population in order to get correct numbers. Yeah, something like that. And so the next stuff here is partition into classes. So this is basically this here has to be 1 if you sum it up, and this tells you, well, the percentage of the different classes that we have. So we have 24% children here, we have 55% adults, and 20% elderly or middle-aged and elder people. Yeah, so the elder people are adults, of course. Sorry for that. Yeah. Okay, so 3 classes, 2 variants. With this population class distribution, you can tell it how many people of your whole population are in the different classes. This doesn't have to be different age groups. It happens to be here in this model. Not that important, but that's the way it works out. Yeah. Okay, next story is contact affinities for the classes. So contacts between classes, this is this Cij matrix that we have here. No? CGL here, or Cij matrix. And this here is written also for the French model here, and here you basically get it with classes. This is classes by classes matrix. And you see that this is not symmetric because, of course, well, there's a higher percentage here than in the other way around. This is due to, as I said, the probability that an elderly sees a child, I guess, is higher than that the child sees an elderly person, or vice versa. I mean, I would have to look it up here how this looks like exactly. Basically the first value shall be children, and then it goes down. So yeah, so that's the way it is. And the story here is that that you have different affinities to have different class interactions. Because the way here is that the middle, that these people see each other, it's like 10 times almost than this here. This is so that's basically the way it works, yeah? And this is not symmetric because, as I tell you, as the populations have different sizes, the way this is written out here, it's for one person, and what is the probability that one person sees one person of its own class, or the probability to see a person of another class, yeah? And this is of course a class by class matrix here, yeah? Okay, so this are the contact affinities, yeah? Okay, then next thing that you have to parameterize, so you just put these numbers afterwards here. So I always did this here with these matrices, that I just introduced another space. This doesn't matter if you put another more spaces in here. You just have to put enough numbers here so that you get to classes by classes, yeah? And this is always row wise. So this here is the first row, this here is the second row, and this here is the third row, and that's basically how it's written. And that's basically how it works with all the matrices in this input file, yeah? And you just have to keep the correct words here. So Cij, this is Cij, these are the contacts between classes, okay? Okay, next thing, initial fraction, also initial fraction in E, yeah? Here the word is initial intermediate fraction. So here you have classes in rows, variance in columns. That's the way it's read in. So this is the first class, first variant, second variant, second class, first variant, second variant, third class, first variant, second variant. And here this is basically, so these have E minus 5, yeah, so very small proportion. So this is basically when the variant is introduced, what is the initial E fraction. So when you go in here, what is the initial value here in E, yeah? That's when you start the simulation. That's what it's about, yeah? Okay. Of course, the way this is written down here, we would probably have them here at 0, 0, because we have the same introduction and one comes just later, but that's not a big deal. So basically that's the way it works, yeah? Second, the initial I fraction. So initial I is just the same for I here. So how are in these I's classes and variants introduced? No, so you have it here. So the I, no, how many people are in the I at time 0? So that's basically how it works, no, for each class and each variant, yeah. So cross immunity, so here we have full cross immunity. Let's make it a bit more interesting. We can vary this later on so that we can see the effects, or just you put it in here. So let's say we don't have full cross immunity, so this is a variant by variant matrix, of course, as we have just seen it before. So if you have this epsilon ij here, no? Which tells you if you get infected by variant 1, how much immunity infers it to you to variant 2. So let's make this to 0.5 here, no, and something like this 0.51. So this should be symmetric somehow, probably, yeah. That's the way you can model this. Here we have two variants, so we have a 2 by 2 matrix, yeah. That's what you need to know. Pre-immune fraction, so these are the people, how many people you pull out of S at the start and pull them into R directly at the start. So this is basically how many people are in R at the beginning. How many people you pull out of S, so to increase this R section here. and this value is also plugged into this f here, no? Because here, as I told you, if you read here correctly, you have here fi, so you have here per class you have pre-immunized people that you can pull in here, and this is basically this. So this is how many people in this class are in R. Yeah, this is not Fij. Could have been done in this model. The way it works, you have it just per classes. Yeah, that's the way it's implemented. Sorry for that. Yeah, maybe one day we put this here with ij, and we plug this in so that you can start off with different things. Yeah, but that's the way it works. Okay, infection affinity for classes. So as I told you, we have. This is the sigma term here, no, that we had here, just to not to forget it, no. So we have the sigma here in the beta term, so which is where one is a class index, the other one is a variant index, yeah. And as I told you, this is the different. This is basically different classes can exert a different susceptibility to the disease. So this models basically the beta for each class against each variant. And so here we have these three classes, and you see that what you do here is basically that in this case here the children seem to be less susceptible, while the others are susceptible here. And this here goes into the sigma, and for both variants it's kind of the same, but we have different susceptibilities for different classes now for both variants. So the matrix is variance rows, so this is for the first variant, class 1, class 2, class 3, second variant class 1 is just 3 now, and it modulates this R. So the R basically then becomes the sigma jump for each class, no? That's the way it works. And then we have these rate constants. So we have one rate constant per variant. Yeah. Also here we could have one rate constant, not just per variant, but per should I say it per variant and per class. Right now we have it per variant. That's a bit a pity, yeah, but that's the way the simulator works. Yeah, so if you want to extend on the simulator, you can change this. The code is open source, so here we have implemented it for the immune drain. For the immune drain, we have one per class and per variant. So basically the idea is here that you can, like if you're an elderly person, you can say, okay, I lose the immunity against the virus way quicker than a younger person, or vice versa, or something like this. You can do this, yeah. But for the conversion rate and the recovery rate, so the delta and the gamma in here, so let's go back over here for the delta and the gamma, we have one per, we have a rate per, you have in the model, you have a rate per variant, yeah. Don't have a rate per class, yeah. So this value goes for all classes. Here too, yeah, this goes for all classes. For the eta, we have one for each, yeah. That's the way it is. So if you go here to the smaller here, see this here is delta I, gamma I, and here you have eta I j, so that we can basically, here we have it for classes, here we have it just per variant in here, these little, so how much goes out of here, how much gets in here, how much gets out of I, and gets into R, and then how much gets from R to S. That's the way it works, yeah. So here we have it just per variant, here we have it per variant and by class, yeah. And as you see, one value per variant, so you put these two values here, and here we have basically an eta. So the eta is this going back here, the eta is the immune waning constant, no? So let's write it out correctly. So conversion rate is the delta value here, yeah. This here is the gamma value here, so how fast, so the bigger this value is, the faster people get over here. The bigger this value is, the faster people recover. So actually you have to measure that, or you have to find that out for the disease that you want to model. Of course you can do all kinds of things to find this out. Either you read it in papers, either you fit these values. This is what we've done for the article. So you can run this multiple times and of course build things around it and fit these values. Yeah, that's the way it is. It's a simple text file where you can replace those values if you want to and run this simulation. Then we have the vaccination. Here with the vaccination, just put this to 0, 0, 0, then it's turned off. But the only problem that you will have is, as you have 2 variants, 3 classes, sorry. So we have here 6 values. That for all these other values you have to have enough values. So you just basically what you do is these are all 6 values, so it's very easy to keep it up. So if you change this here, you just multiply this out and you put the same values here back, so that you have enough values that the program doesn't crash, because of course it reads these values in and otherwise it will crash. Yeah, so you have to put enough values there, but just keep it off with 4 zeros in vaccine logistic maximum, then it will stay, then it will have no influence on the calculation at all, and you have the equations as they are up here. Okay, so we got our little platform here. So we have 2 variants, 3 classes. You have here described what everything does. You have here the model as it's built. I hope you got it. I hope I have explained it and in enough detail. Let's run this. No, so this is our input file. Once you have your input file, everything that you have to do is just to basically to run this here. So how do we run this? Of course, we have this input file, we have edited it, we have put all our values in, or we have changed the values to the values that we wanted to have. I hope that this is also very nicely described. So I made an effort that in the published version you have here a 2x3, so that this is not 2x2, and so that you understand basically how these values look like. And that you have here a description, well, what is in the columns, what is in the rows, how is this turned out. You have to be careful, because sometimes here, for instance, in the sigmas, it's the variants which are in the rows. Here the variants are in the columns, but basically I made here a description how to write this down every time. And the rows, of course, this is row, and in the way the syntax that I use here is that I always make 2 spaces from one row to the next. Yeah. Of course, if you just make 1 space, it's fine, but you have to have enough values, and so this is row wise then. Yeah. Okay. That's the way you format your input file. Once you got this input file, you can simulate. And you get a simulation out of it. So let's do this. I will just put my editor in the background here. And so as we have compiled this just before with our little GCC compiler here, we can do something like execute mol, and the input file, of course, it comes here with this stuff here. And you can modify all this according to the parameters that you want to have. And I can run this here and say, well, execute mol, no? So simple sample input, and then I get out lots of numbers, and you will say, well, what are all these numbers? And these are basically the output of your simulation. No, that's the way it is. So these are tabulated tab separated values. The first value is basically where you're in time. So here we have runtime 730. So let's store this into a file. Let's use this little operator here on the shell, on the bash shell, which basically makes a file redirection into an output file, and let's put this into temp out so that we have this in a file and that we can plot this, no? So that's basically what we want to do, no? And how can I plot this? So I can just use GNU plot, for instance, and the way this works is that the first column, as I told you, is the time. So let's write it down how this works. Yeah. So if I have here my little, let's say, let's get here to this here. So how does this work? So I have 6 variants, no? Okay. Okay. And so the stuff that this works here is the first column is the time. So then I have a tabulator and I get to the second column. Yeah. So here I can't type a tabulator, and the second column is basically S of the first group. Yeah. Of the first group, first variant. Okay. Then I have S of the second group, first variant. Yeah. S of the third group, first variant, because I have just 2 variants, 3 groups. That's the way it comes out. And then I have the same thing here for the second variant. Yeah. Okay. So 6 columns. Okay. And then the same stuff goes for E and for I. Okay. So then I have this is the S matrix. And then I have the I matrix, no? Sorry, then I have the E matrix here. So these are all the infected I'm worried because I have the feeling I made something wrong here. Yeah. This here is S, this here is E. E second group, no? Yeah, E1 second variant, E2 second variant, E3 second variant, no? So that's the way it works. So you have 6 values, of course, for the S compartment, 6 values for the E compartment, and you have 6 values for the I compartment. Afterwards, and then you have 6 values for the incidences. Yeah, so the incidences is basically the gamma in, and this is basically how much falls in here, no? So this is how much susceptible get infected. So this is like the delta times this E term here. Yeah. If I say it right, so this is the incidence and this is then accumulated. Yeah, these are like the next values. Yeah, so this is the accumulated incidence that you have here. So it's basically how many you pull out of the S compartment all the time. Is it that way? Yeah, it should be basically that way. So it is the incidence value. Yeah. Okay. The next 6 are the incidence values. And then that's basically it. Yeah? That's your trajectory. And then you get out still some 0 values, because these are basically how many people are in this vaccination compartment. But basically in the vaccination you're not really interested. Yeah, I just will make sure that I don't tell you some crazy stories. Let's get here this epidemic up here. What we pull out here, how are these compartments built up? So first we have the S compartment, then we have this I E compartment, the I compartments. Then we have this inc compartment. So the inc compartment are conversion rates. Okay, so the incidence rate is delta. So these are, so you have like the E's. Okay, you have like the E's. I will just copy this here, paste it here. So this is all in one row. I will just pull it over so that we get this here. This is all in one row, tabulator separated. And then the next 6 values that you have are basically the I's. So I will change this here quickly from E to I. And then you get 6 values which are the incidence values, and the incidence values are basically these E values. Yeah, the current conversion rate times the E value. Yeah, so it's the gamma I. No, conversion rate is gamma E conversion rate. That's okay, so that I don't tell you something wrong. What is the conversion rate? When I go to I have conversion rate E. So this is basically the incidence. This is this part here. Yeah, this is the incidence that we pull out here. Yeah, and that we plot here, that you can read out here. And this here gets dt d in. So this is a compartment, and this basically gets here. So this here is the derivative of that, and so this is just basically the sum of all these incidents. So if you integrate this value here, that's what we call the incidence. Yeah, okay. And these are the next 6 compartments here. So that's the way it works. So you have here then incidence values. So incidence 1 for the first group, first variant. And then of course for all these, and so I will just copy this and paste this, and this is basically the way your file works. So the way your trajectory works. So you have like here, let's modify this for you. So we replace this here from I to incidence. So as I told you, the incidence is, so inc, yeah, it's the integral of delta times E. Yeah, E from T. No, of course. Yeah, that's basically these incidence rates. Yeah, that you get out. Yeah, okay. These are important values for the epidemiologist. If you want to know how many people are infected, you just sum E and I up. This is basically what I find the most interesting personally, but that's the way it works. Yeah, and then due to the vaccination stuff in the file, you get like 6 zero values down here. No, and so you can read this and plot this for all these little compartments, and so you know, okay, how many children are infected today. So you take the E value and the I value out of at the right time coordinate. So the first value is the time here, no, and this is all tabulator separated in one line, and that's the way it works. Yeah, so that's what you get out of this file, and this is what we get here with this. So this is basically one line. Yeah, so you see here we are at, yeah, I canceled this, yeah, but here you see we are at time 640 days, no, if I read this right. And here, well, these are basically the values in all these different compartments that we have. And if of course I want to have the total infected people, well, I just take all the E and all the I's and sum them up and plot them. Something that you can do. Well, you can do this with Python or whatever, and that's the way it works. Yeah. yeah, that's the way our epidemic simulator works. So far so good. Let's go to plot it. No, how can you plot this? So one way to do this is you use an IPython notebook if you have it, or you just use gnuplot. Yeah, so I can use gnuplot here. I will just show you this for a very small presentation, and then we will do it with an IPython notebook. No. So gnuplot, let's use gnuplot in order to do this. So this is basically the output file format, so all on one line, as I told you. Yeah. Let's put the incidence over there so that this is like that, and let's put this all into one place. So how does this work right now? No, so yeah, let's do it like that. No. Yeah, okay, right now we got everything messed up here. So that's our file format, no? And then we have like 4 zeros and all this is on one line, no? Nice, no? If we get it formatted right, no? Something like that, no? Okay, yeah, so time in the first row, this in the second row, third row, fourth row, and this is group-wise and variant wise, no? So that's the way it is. So the columns, you have the groups, then you have the variants, and this is all in one line. Yeah. Okay. So plot this. So for example, if I want to plot, well, let's say according to our epidemic, let's plot of the adults here. Yeah. Let's say the E and the I value, no? So the E and the I value of the adults of the first variant, no? So I take this here, plot, and so one, of course, so I have my file, which I put into, did we run the epidemic right now with the redirection parameter? I guess so, no? Yeah. So we redirected this, just to remember it, into this temp out file. Very nice, yeah. And we have it there. So if I do this, just put I missed the T, it doesn't matter. And so I can say 1, 2, so this is then 1 first row, and so here I want to have the adult, so here I'm 2, 3, 4, 5, 6, 7. Yeah. 3, 4, 5, 6, 7, 8. I want to have this one here. So 1 to 2. So this is like this one here. 1 to 7. What was it like? 1, 7, 2, 3, 4, 5, 6, 7, 8. 9, so 1 to 9, okay, because I want to have this here on the x-axis, this on the y-axis, no? 1 to 9, yeah, and it will get us here, and I want to have this second one, so 1 to, what is it, 9, 10, 11, 12, 13, 14, 15, no? Am I right here? And the way gnuplot works, you have to do it like that. And then I get my 2 curves. And they're almost the same. Yeah, but that's basically the way. Oh, there's an unrecognized token. Why is there an unrecognized token? So something went wrong here. Hang on. Something went wrong here. You have to type here using, so with a U, so that you get the right columns. And here we got it. So this here is basically for the let's say for the adults using this epidemic. So you have this typical epidemic curve, and here, of course, due to all these interactions, these kind of things here. So this here is the 1 to 9 is then the E, so the people in the E place, and this is the people in the I place. Yeah, and this is basically how your epidemic goes. And if you want to, you can sum this up, and you get your number of infected people during the whole epidemic, and that's basically what you get out of it. Yeah, that's how it works. Yeah. for these two groups. And of course I can select, as I just counted with you, different groups and have different plots and plot this in all kinds of ways and script this here with gnuplot or something else. That's one way to work with that. Another way to work with that is of course with an IPython notebook, which might be a bit more convenient. We can do this the same way here. I will show you how this works. But that's basically how it works. And here you have your one result out of this simulation. And if I want to have another result, well, basically let's do this, for instance, for let's say for the elderly here. For the elderly, I just have to increment this once. So 1 to 10 and 1 to 16 then, no? If we count it right. And this is the same thing here for the elderly population, no? Not sure how far we got, but maybe here the peak is a bit different, no? That's basically where we have our multivariant, multi-class simulation with the parameters that we have in this input file, that of course you can adapt to whatever your needs are. And I hope that you find this useful, yeah? So this is a tabulator separated file with where you have all these values in each column that you can basically read in. Then you have in this last part here, you have these incidence values. And let's do this with an IPython notebook, no? So that you see that how easy it is to read this file, no? So let's do this here. So in order to do this, you need an IPython notebook installed. You refer to your distributions manual how to do this. You also need pandas to have installed, so either you use pip install pandas, something like this, yeah, you will find it out, or pip3 install pandas, depending on your distribution. And you need an IPython notebook to do this the way I do it here. You can do this in Python, whatever, but this is just to give you a rough idea. So I will start out my Jupyter notebook here, Jupyter. So right now it's not called IPython notebook anymore, it's called Jupyter notebook. So that's the way it is. I don't use the browser because I do this in Emacs. You can do this in the browser, yeah. So if you want to, it's basically the same story. You will see this. So I do no browser here because I have the iron tool in Emacs, yeah. You can do this with let's do it with the browser so that we do it just the way you do it, yeah. So that's basically, we have this Jupyter notebook here that's coming up, and which will launch my browser or not, yeah. Here comes my browser, and I have a Jupyter notebook, and I can say, okay, I want to have here a new file, no, something like this, new IPython 3 call. So you can do apt-get install Jupyter, something like this, in order to get something like this up here. And here I can say, well, what do I need in order to do this? No, import. Let's import pandas. No, as pd, and let's import. It's called matplotlib. No, matplotlib pplot. No, something like this. As plot, no, so that we can do some plots with that. All nice, all good, no. And then we run this here, so then we have some functions that we can use. And using pandas, I can use data frames and stuff like that. I hope it runs, because yeah, it runs. So we have pandas, we have the matplotlib. You don't see me anymore because the browser is so big. I make this a little bit small so that you see my little face. How nice, no, that you're not lost. So cute. So we have this, and the story basically as it goes is we can do something like this. We can import this as a data frame. And how do you do this? So you use pd from CSV, no, that's the way it is. Why don't I have autocomplete here? Yeah, I hope it works like that. And I need my file here, which is temp out, yeah, and then we have a separator, which is this one here, and we run this. No, it's not called from CSV. What this is called in pandas. This is really stupid here. Pandas. Normally I have here read CSV. No, sorry. So read CSV up, and you need this tabulator separator, and then you have, if I type here df, I get this out here. No. Yeah, and so these are basically, the problem is that he believes here this is the header, so you have to tell him here also header equals none. Great that I plotted this already. And then I have my data frame here, and we get here correct description. So these are 0 here, and I can say that I want to have my data frame set index, I guess it's called, and I want to have this 0 column here as my index, so that this here basically is the index. That's a time variable, of course, and then I have, as I just told you, here this little the way this is described. So I could basically name this and say this is the header here, no, but just use this here as a variable. But we won't do this because we can count, no, and we know what we're doing here. And just to tell you that way it works. So if I have this right now, I still don't have the right index. Let's say df maybe. Yeah, right now he got it. Now we get the index is this the 0 column, and we see that basically this here is the time, and this here is basically then the values in the different compartments, no, that we have turned out here, which are written in this let's say in this order here, no. So the first number 1 is then this here, no, and number 7 is then this here, because we have 6, no. So if you have, of course, more variants and more compartments, then this here is longer, yeah, in this way, but that's the way it works. And so you basically, I can right now use the matplotlib, so I can do something like this. So x is df 0, let's do it like that, no, and then we can say y is let's say what are we interested in. We can do something like that. So we want to have like the incidence, or let's say the total infected. So let's say this is 1, 2, 3, this is 6, 7, 8, no, df8 in this respect here, because in the other ways this was not 0 but this was 1, so that's why we are right now 1 off. And we can say we want to have 8 and df9, and then we know how many people are infected in total in this class, in the second, in the elderly, in the let's say not in the mid-aged class here, no, in this respect here, no. And so this is it. So this was then 8 plus 6 should be 14, if I'm not wrong here, no. Let's be sure that we don't make anything crazy here. So we are here 1, 2, it's 8, 9, 10, 11, 12, 13, 14. We're correct here, no. Let's do that like that. This should basically work out. I hope it works out like this. And then we can do something like plot, plt plot, and we can say x, y, no, something like that. Let's try this out. Maybe this does not work. I'm a bit worried. And if I want to have df0, I can't get it because I set the index here. So basically I shouldn't have done it. So we'll just reread this here. We don't set the index. I'm sorry for that. So you have learned something here. So df0, then I get the 0 column with these values. We don't care about this, but then I can do something like, we just put this away here. would have been convenient, but the way what I can do right now is I can do x and I can do y, and I can say this was df 8, no, that's the way it was. 1, 2, 3, 4, 5, 6, 7, 8, no, and the other one was 14. That's fine, so we can try it like that. I'm not sure if this will work, but the way what I just wanted to show you is that you can basically play around with this then and do x and y. And here we have basically the curve of infected adults in our simulation of the first group. So basically this one and this one summed up, and we get the curve basically from the data here. And you can of course play around with this with all the values that you have in the resulting trajectory file that we have written here to temp EO. And I guess we will stop here with this little tutorial, and I hope you found that interesting. And I'm sorry for this little hiccup here at the end, but I don't want to make a new movie out of this, and I hope you're really happy with that. So thanks so much, and have a nice evening. That was it for the tutorial on our little epidemic simulator.